What is structural equation modeling? Structural equation modeling, or SEM, is a statistical method used to test relationships among multiple variables simultaneously, including both observed and latent variables. It combines factor analysis, to test the measurement model, and path analysis, to test structural relationships, allowing researchers to examine both direct and indirect effects at the same time. SEM also accounts for measurement error, making it a powerful tool for testing theoretical models. SEM is essentially a combination of two models, the measurement model and the structural model. First, the measurement model, which is tested using CFA, examines how observed variables, such as survey items, measure their underlying latent constructs. This step ensures that the measurement instruments are reliable and valid. Second, the structural model, which uses path analysis, examines the relationships among the latent variables. It tests the hypothesized direct and indirect effects to determine how one construct influences another within the theoretical framework. In short, CFA tests how we measure the constructs, and path analysis tests how the constructs relate to each other. What is PLSSEM? It stands for Partial Least Squares Structural Equation Modeling. PLSSEM is a variance-based statistical method used to estimate complex cause and effect relationships. It is mainly used for prediction and exploratory research, especially with small samples and complex models. Its key features include 1. Focuses on maximizing explained variance, R². 2. Best for prediction and exploration 3. Works well with small samples or non-normal data. And 4. Handles complex models easily. Main issues related to CBSEM. First, CBSEM depends on strict statistical assumptions. It usually assumes the data are normally distributed. CBSEM also works best with continuous data, which can be a problem when using Likert scale survey items that behave more like ordinal data. Second, CBSEM typically requires a large sample size to produce reliable results. Researchers often recommend samples of 200 or more. Third, CBSEM can encourage too much focus on model fit statistics. Because many fit indices are available, researchers may be tempted to modify the model just to improve fit. This can weaken the theoretical meaning of the model if changes are not well justified by theory. When do you use PLSSEM? I would use PLSSEM when my goal is prediction or theory building rather than just theory testing. Its main strength is its ability to handle non-normal data and small samples, though it is often critiqued for its lack of global fit indices and a slight statistical bias in its estimates. CBSEM, covariance-based SEM. CBSEM is a theory testing approach to structural equation modeling that focuses on examining how well a proposed model fits the data. CB-SEM usually requires a large sample size, assumes the data are roughly normal, and is mainly used to confirm and test theories, allowing for rigorous testing of global fit. Key features of CBSEM. Used mainly for confirming theoretical models. Emphasizes overall model fit. Requires larger sample sizes. Assumes normally distributed data. Main issues related to CBSEM. First, CBSEM depends on strict statistical assumptions. It usually assumes the data are normally distributed. CBSEM also works best with continuous data, which can be a problem when using Likert scale survey items that behave more like ordinal data. Second, CBSEM typically requires a large sample size to produce reliable results. Researchers often recommend samples of 200 or more. Third, CBSEM can encourage too much focus on model fit statistics. Because many fit indices are available, researchers may be tempted to modify the model just to improve fit. This can weaken the theoretical meaning of the model if changes are not well justified by theory. The main differences between PLS and CB lie in their purpose, focus, and data requirements. PLS is mainly prediction-oriented. Its main focus is on maximizing explained variance, meaning it tries to explain as much of the dependent variable as possible, usually measured by R-squared. It works well with small sample sizes, makes fewer assumptions about data distribution, and is more flexible. Because of this, it is often used in exploratory research or when theory is still developing. In contrast, CB is theory testing-oriented. Its main focus is on model fit. In other words, how well the proposed theoretical model fits the observed data. It typically requires larger samples and assumes normally distributed data. It is more strict and confirmatory, making it suitable for testing well-established theories. In short, PLS is more suitable for prediction and exploration, while CB is more appropriate for theory confirmation and model validation.